This talk was originally presented at NASA AbSciCon 2012 at Georgia Tech in Atlanta. I assume everyone is familiar with the Drake equation, which is used to predict the number of detectable intelligent civilizations. When Drake first coined it in 1960, there was little evidence that n would be much greater than 1. But now, with the detection of solar systems common, an expanded definition of habitable zone, life showing up in more and more extreme environments, and other advances seen throughout this conference, the number of detectable civilizations could easily be 100 million. When you have a sample point of 1, us, statistics tells you to assume that you are at the midpoint, so we can assume that at least half these civilizations are more advanced than us. Since we have already begun to communicate across space, we can assume that many of these civilizations are communicating across vast regions of space. In 52 years of searching by SETI and others, we should have detected at least one signal. Well, we have the famous wow signal, but of course it was a false alarm, so we can safely say at this time that we haven't detected any signals, and we have to ask the question, why? The answer may not lie in the lack of intelligent signals, but in the manner in which we choose to search for those signals. Albert Einstein, building on the work of Maxwell, Lorentz, Michelson-Morley, and others, published his special theory of relativity in 1905. In this work, Einstein took the measurable velocity of light in free space, 186,000 miles a second, or c, to be an absolute. The problem with this is that we assume the EM signals propagate only at the speed of c. So we limit our searches to magic frequencies that travel great distances through space without getting absorbed or obliterated. We ignore the possibility that other civilizations transmit signals at many thousands of times c, immune to the effects of the interstellar medium. So we have to ask, is this a possibility? And if so, why do we restrict ourselves? The velocity c equals 1 over root epsilon naught mu naught appears in Maxwell's equations, but these equations say nothing about that velocity with respect to an absolute background and give no reference frame against which the velocity is measured. All experimenters obtain the same value for epsilon and mu naught, so the observed velocity is the same in any observer's reference frame. Since the speed of the moving observer can assume any value, the EM energy or wave leaving the source must have speed components in a continuous range, including c as measured in any arbitrary reference frame. The reference frame independent nature of Maxwell's equations does not prohibit a range of velocities, but instead dictate this to be so. To see why, let's consider two observers, Alice and Bob. Each carries a long rod, say 1 light second or longer. Alice is further away from an imminent event than Bob. The event will be an explosion that leaves a burn mark on the end of each rod and sends light traveling toward the observers. Clearly, Alice sees the light later than Bob, and the time from the event to its observation is given by the length of each rod divided by c. As we see, t prime is greater than t. Now we consider Alice and Bob in relative motion. As far as each observer is concerned, nothing changes. Alice still sees the light at time t prime, Bob sees it at t. Even though Alice is next to Bob when she sees the light, he has already seen it. Now it's easy to say, wait, Alice is moving, so that changes everything. But motion is relative, as anyone who has ever told their child to sit still in a car moving 60 miles an hour down the highway knows. So we can look at the same situation from Alice's perspective, where she's stationary and Bob is moving. There is no denying in this example that Alice will see the light after t prime. Yet this situation is no different than the first, since we have no way of knowing who is actually doing the moving, whether it's Alice or Bob that's moving or Alice or Bob that's stationary. We can even situate ourselves in such a way that both Alice and Bob are moving. Clearly their times don't depend on our status as a disinterested third party to the experiment. Einstein made an assumption that Alice and Bob will see the flash at the same place and at the same time, and this forced him to make some unusual corrections to the Galilean transform. The problem is that if Alice and Bob see the light at the same time, then the speed of light is not c for at least one of them. The first thing Einstein did was to tell Alice that all her rulers were wrong. In fact, all lengths in her reference frame have shrunk, proportional to her velocity given by gamma. In addition, all her clocks, in fact time itself, has slowed in her reference frame, so that she is measuring time differently. But by making these corrections, we can now establish a picture whereby Alice and Bob see the light at the same place and same time. The problem is, Alice and Bob can now no longer agree on when and where the event occurred. In fact, two events that are simultaneous for Bob may not be simultaneous for Alice. So we have to ask, can we get to the special relativistic transforms, starting with the Galilean transform, and determine, therefore, what, if anything, the special relativistic transforms actually mean? This slide shows the Galilean example we've been considering. We'll establish that t equals 0 when Alice and Bob are at the same location, so the event itself happens at negative t. Thus, the relation between x and x prime is given by the usual Galilean expression. We have already derived expressions for t and t prime, and Maxwell gave us the expression for c. In a Galilean framework, the expression for c and the Galilean transform tell us everything we need to know. But we can play around with these equations to get some interesting results. We start with the Galilean transform and substitute the expression for t prime. Performing some simple algebraic substitution gives us an expression for x prime in terms of xt and gamma, where gamma is defined as before. We can take the same expression for t prime we just used. We can develop a similar expression for t prime in terms of xt and gamma as well. Now at this point we're still dealing with the Galilean transform, and these equations are perfectly valid, even though the form is different than what we're used to seeing. But Einstein took both sides of both of these equations and divided through by gamma to obtain a contracted value for all lengths in Alice's frame and a dilation of time in Alice's frame. So we're left with two expressions for x prime bar and t prime bar, which we will call the special relativistic transform. These expressions have meaning as long as we take them only as the ratio x prime bar to t prime bar, much like we can say that 12/9 equals 8/6. But if we try to establish independent meaning to each term, for example saying that 12 equals 8 or 9 equals 6, we run into problems. Likewise, if we try to ascribe independent meaning to x prime bar or t prime bar, we run into problems, even greater than the loss of meaning of the term simultaneous. For example, we create an artificial limit on the speed of light at c, and we also limit the maximum attainable speed for matter or energy to c as well. But what we have to keep in mind is that this entire derivation was just an algebraic manipulation of the Galilean transform. There is no physics here. Further, Einstein's assumption has never been tested. So what does any of this mean in terms of the search for extraterrestrial intelligence? Well, as we have shown, there are detectable components of any signal that reach any observer both faster and slower than those that arrive at the speed of light, or c. These components can be many thousands or even millions of times faster than c. Advanced civilizations are likely filling the cosmos with signals that we just aren't looking for. There are many more interesting results from the Galilean treatment of light signals. I mentioned that superluminal signals would be immune to the effects of the interstellar medium, for example. But there's also the possibility of encoding massive amounts of data into a much smaller bandwidth than possible under ordinary conditions. So we have to ask again, why haven't we detected any signals? As stated before, the answer may have nothing to do with the lack of intelligent signals. It's just that our current technology may resemble looking for smoke signals in New York and concluding there is no advanced civilization there when everyone's walking around talking on cell phones and using Wi-Fi instead. Thank you for your time. Feel free to write with questions.